Now, as we saw with left-hand rule and then trapezoidal rule when we looked at numerical integration, there's other ways to do this kind of numerical differential equation solving, or calculating slopes. If you look at what the pattern is, hey, we used one value to estimate the slope for Euler's method. We used two slope estimates when we did Hoyne's method, and presumably if we used more, we would get even less error happening as we go through this. The ways we can do that and slice and dice our values and get different slopes in different ways, the family of methods that uses this is called the Runge-Kutta methods, sort of pronounced sort of Germanish where you say all the letters. Runge-Kutta methods. And the idea is Euler's and Hoyne's are examples of this more general method. They all have the same basic structure. We always move by a delta t if we're talking about constant time steps. So the t's always go up by delta t every time. What we get in terms of our delta y is our interval size and some kind of slope estimate and then an averaging coefficient. So when we had Hoyne's method, we had the average of f of ti yi plus f of ti plus 1, Euler's prediction, y tilde we called it. But the idea is that we had two slopes and then we averaged them. And we could have three slopes and divide them by 3. That would work too as a Runge-Kutta kind of method. It wouldn't be the best. It turns out the next natural step is, actually let's skip that over. The next natural step is order 1, order 2, order 4. That's the easiest one to develop. And what happens here, we've got Euler's method, just follow the slope. Hoyne's method, follow the slope, get another slope, average the slopes. This is the real prediction here. This is our real estimate about what's going on. Runge-Kutta does some sort of variation on that, but it cuts things in half. It uses like a delta t over 2 and a delta t over 2 here. So it does little half steps. Anyway, it's not that bad graphically. The idea is we're going to get 4 slopes by mixing and matching some of these terms, and then we'll average them somehow. This is actually how it does get averaged out. This part here you can Google, you find it pretty easily. What I wanted to focus on today is this last part. There we go. This last part here. My new y on the left here is my old y plus. We see a 6, we see a 1 and a 1, and there's 2 s's here, which if I added them up together would be 4. What does that sound an awful lot like? 1, 4, 1 divided by 6? Simpson's rule, exactly. So again, when we integrate, doing integrals, then we got Simpson's rule. When we're doing differential equation solving, we're actually integrating just with a more complicated scenario. So it's not too surprising that we see something that looks an awful lot like Simpson's rule when we come down to it. So this is the generalization of Simpson's rule. So if you want the parallels, left hand is Euler, corresponds to Euler. Hoyne corresponds to trapezoid, and this fourth order Runge-Kutta method corresponds to Simpson's rule. They're the closest analogs. And that's actually a pretty powerful observation to recognize that we're not doing something really, really different here. We're visualizing it a bit differently, but it's the same underlying calculations. We also remember the Simpson's rule was pretty good. Simpson's rule did so well that we said it's not even worth going much past there with finite or consistent step methods. And the same applies here. Let me see if I can zoom in on this graph, make it a little more. Is that going to work? No. Let's try the old-fashioned zoom. Where's the zoom button? Zoom, search. There we go. Buttons. There we go. So that's a little bit more obvious. If we look at, it's actually swooping a bit. The blue line's the real solution, and the green line, the straight lines here, are the Runge-Kutta order 4, so that's Simpson's analog. And if you ignore what happens in between, the green lines the green dots are almost exactly where they're supposed to be. So the fact is we're allowed to take such big step sizes, and we still get super accurate agreement between the prediction of the Runge-Kutta and the blue that in fact we actually need more skill or technology in between the points than we do just to get the points right. We probably want to use a spline or something nice and smooth to go between them rather than straight lines. But we can definitely see that Euler's method down here is kind of cruddy. Hoynes method, it's better, but not as good as this green line solution. So again, Runge-Kutta order 4 has that sweet spot of being not horrible to calculate. We can see the formula back here. You know, it's 4 lines of code, but it's just type these into MATLAB and use it. And it gives us performance that's pretty powerful, pretty effective, high efficiency. And so like Simpson's rule, that is the technique you'd use most commonly in practice. Basically, it has that combination of sweet spots of not too complicated, but much better than the simpler alternatives.